So thank you very much for joining and staying up before the lunch break. I will try to keep you up until we, not lunch, the coffee break actually. Lunch was, the second day is setting in, so we need to be more focused. This is about image live migration, live import, and instant restore. It's about Ceph RBD. It's work that I did together with my colleagues, Effie Ofer and Orozeri, were all from IBM Research in Haifa, Israel. My colleague Effie said, add it's alive at the beginning, spice it up. I'm all for adding some excitement. So at least maybe if it caught at least one more person, that was worthwhile. So basically, what is this talk about? It's about a feature called image live migration. A bit on the timeline of the feature. So it's been around for a while. It started in Nautilus. In Nautilus, it was only migrating an RBD image between two pools in the same cluster. The reason was mainly if you want to move between erasure coded and replicated, for example, or some setting change and you want to keep your image alive but move it quickly. In Pacific, this was extended to external sources. Now, I'll be talking quite a bit about this. I don't think this ever got a decent Cephalocon advertisement. So even though we did not do this actual coding work, we did take part in kind of the specification for it. So I'll give it some rap here. And there's two changes that we did do that are in the pipeline. One is for Ceph to Ceph cross-cluster migration. The other is an external NBD source. So I'll be talking about all of these. So this is the timeline. One important note, this is only supported by librd. It's a librd function, not KRBD. So if you have OpenStack or KVM virtualizer, this would work. NBD RBD. It will also work with the NVMe over Fabric plans because that's librd based as well, but not KRBD. Okay, so what is image live migration? The idea is to instantly move a volume from one location to another. What do we mean by instantly? You can't move the data instantly, but you want to immediately start working and have data. So you have a target and source, immediately start working on the target, but the data is in the source, you can use that as you go. Basically, it's what's called post-copy migration, known from a number of implementations. And it works in a very simple way. So you have the source and the target. Right now, all we need is the target has to be a Ceph RBD cluster, a Ceph cluster with RBD access. The source, that can vary depending on what we'll be showing here. And it's all driven by the RBD client, which is librd. And the way it works, very simple. If you have a write, you immediately start writing with the target. No writes are ever going to the source. So the writes are directed directly to the target. When you do a write operation, there's only one scenario where you actually go to the source, which is copy on write. If you want to do read, modify, write, small updates, so it's going to read some stuff from the source and write them to the target. So writes go to the target, and that's it. Reads, on the other hand, well, they also go to the target initially. So target is the ruler here. Go to the target, fetch the data. But what if it doesn't exist? And initially, nothing exists at the target. So you either get the data or you get an answer, we don't have it, go to the source and fetch it from there. So it's an added latency at the read, basically, and then depends how far the source is to actually go and fetch it. Within the same cluster, of course, it was typically a very small overhead. So really summarizing, targets do write and read if available. source does read I/O, and there's the migration aspect of it. So there's a background migration process that keeps running in the background. And this pink thing, it is throttled. I don't remember exactly to what extent, but that keeps on going. So at the beginning, you'll get performance which has to go, read performance which has to go to the source. As time progresses, this migration finishes and you'll get the performance of the target. At which point you can also detach the source. Okay, so I wanted to highlight 3 different use cases for this. One is live migration between Ceph clusters. The other is instant import into Ceph, and the third is backup and instant restore. So let's start with the first one, kind of a warm-up. So it's a cluster-to-cluster migration between Ceph. It's just a natural progression from doing a migration of a volume within a cluster. Why not move between 2 clusters? So who is it for? It's for people that have more than one Ceph cluster in their deployment. There's quite a bit of these. Many times it's even within the same data center. If you just don't want to grow your cluster infinitely, you keep creating new clusters to handle your data. And then how about load balancing between them? What happens if one runs out? You want to be able to move data, and you want to not kill the application, so have it instant or basically live migration. The other is you have an image on cluster A, and for some reason you need to use it instantly on cluster B. For example, you need to create a clone of it on cluster B. You cannot clone across clusters. This gives you the ability to basically clone across clusters. You can actually keep it as a clone across cluster without doing the background migration. So just keep the source always there. But this gives the ability to clone across different clusters. So that's what it's good for. The benefits of using this methodology is it's instant, because once you set it up, you can immediately start running with the target. Because it's all done at the RBD level, and the source, the target RBD, you can move all the snapshots with you. All the thin provisioning, sparseness of a volume is preserved. So that's all nice pluses of this method. There are, however, some fine print, so not everything is easy. One is, and this is actually true also for the inter-cluster migration, you need to somehow handle the remap of a mounted volume. So you want it to be live, say that the VM running using this volume, and now you migrated it. You need to somehow change the mapping to another volume. You can potentially, so easiest way is just restart the VM or container or what have you. That's not as fun. There's a way to pause and remap and then restart, basically continue the VM running. At least we did this with libvirt. It requires some code changes to libvirt, so that are not up there yet. So there's some challenges there. This has nothing to do with the cross cluster or anything. Other challenges, we do not support migration of images that are clones. So if in the source you have an image that is a parent and child, and you're trying to migrate the child over, you're going to flatten the child, basically. You're not going to keep the structure of a parent and child. This can inflate space usage. If, for example, you have many children for the same parent and you want to move some of them. Currently, we haven't done a solution for that. Another limitation is that right now it's not upstream yet. The PR is under review. So I encourage people that are interested in this to go and ping this PR and see when is it coming through? That might add motivation to actually go and push it through. I should note there are alternatives to moving volumes between different clusters. You can use libvirt block copy, which does this live for a connected VM. If the VM is not connected via libvirt, it's not going to help you in any way. There's RBD mirroring. There's pros and cons for all of these. I'm not going to go into them in this talk. By the way, we can do this interactive, so if anybody has any questions, feel free to jump in. Okay. So this is our first use case, the cluster-to-cluster live migration. Let's move to a second, which is instant import into Ceph. So the use case is the following. We want to bring images that are currently outside of Ceph into Ceph. And there's a number of reasons why you'd want this. And we want to do this quickly, because otherwise you could just move the volume bit by bit, wait for it to finish. We want to do it instantly. Suppose you have, I'll give some examples here. I have some QEMU image residing on a NAS device. It's your old hardware. You've upgraded to a brand new Ceph cluster. You want to start using your old data that is being phased out. Any block device, SAN, so anything you have out there that is not Ceph and you want to move into Ceph RBD, and we want to do it instantly. So, of course, regular migration, you're going to have to finish until all of the migration is over. You've moved all your data in, and only then you can start running. Sometimes that's doable. If you have a lot of images, typically that's problematic because you're going to have to, some of them are going to wait in line to be migrated. The instant you can start working immediately, even if the data is being fetched actually from the source when you actually need it upon request. So I'll do kind of a, but for this, basically we need the new features. We need live import, live migration from an external source. So let me give a kind of a quick tutorial on what's live migration, image live migration, how it's used, and how the new features work. So this is the basic image live migration from any source. It has 3 commands. One is prepare, which is basically setting up the link. Once you set up the link, you say prepare this volume in cluster A from that volume in cluster B. Immediately you can start running on this cluster. Of course, you need to point to a volume that is immutable. So it's a snapshot. It cannot be changed anymore. Second command is execute. Starts a background migration. And third command is when everything's over, you do a commit, which kind of cuts off relations with the original. You can actually do this when it's not an external source. You can do it with the migration mode that says the commit also deletes the one in the original location. But you can also keep the one in the original location and just cut the ties with the origin. So that's general image live migration. How does it work with an external source? So here, two parameters were added, which are crucial. One is format, and the other is source. So for format, you have basically 2 options today. One is raw, and the other is QEMU. And QEMU has limited support, so I'll get back to that. The source means, so this is how the image is laid out. That's one of 2 options. The source is where does the image lie, and here we have 3 options. File is, so give it a path, local on your machine, full path where the file exists. HTTP is a URL, And S3, actually, you can give it access, so you need credentials to S3 interface and the pointer to the service itself. And now you can do any combinations of the two of them, of the three of them. So there's more information. Again, it's available since Pacific, and there's extensive documentation on this. So let's do an example. I mentioned we have a QCOW2 image residing on some NAS storage. What you can do, and this makes a lot of sense, so you mount the file locally, the QCOW2 file, and then you run prepare where the source is file, and you point to the local file, and the format is QCOW, which is QCOW2. And that's nice and clean and helps us out. For whatever reasons, we couldn't actually use this. So the reasons are mainly the QCOW2 implementation is limited. For example, there's no compression support. There's no backing file support, which was in the use case with the customer we worked with. This was a big thing. They needed the backing file support there. And it's also limited to QCOW2. That's the only format that was implemented out there. So we'd want to be able to extend beyond that. These are the limitations. So that's option one. So we tried out another option, and this is the second option. So let's use QEMU NBD to mount the volume locally as a block device. So I'm going to open parentheses, give you 2 minutes about NBD, and we'll return here. So a bit about NBD. NBD is network block device. A lot of you would be very familiar with this. It's been around for a while. It's a very simple protocol for interacting with the block device. It's not something widely used like iSCSI or NVMe over Fabric. It's something much simpler and more basic. It works by setting up an NBD server that listens on a port, and then you can put an NBD client, talk to it, and access the block device through it. So that's, again, a very simple protocol there. The main use of NBD today is for bridging the kernel user space gap with block devices. So we don't have a fuse for block devices. Rather, what people do is create a user space NBD server. There's a KNBD client sitting in the kernel that can then expose your block device as a local device mounted on your machine. So that comes in handy, and there's examples of this. So RBD NBD is one way to use RBD in a kernel environment, mounted locally. QEMU NBD is one that's more flexible. It implements a lot of things. This is the reference implementation of QCOW2, basically, and it supports all functions, etc. So our idea is to use QEMU NBD here. So back to the original slide, I said let's mount the volume locally with QEMU NBD. It supports all the QCOW2 features. It's good. So now we have it at a file location, and the format is no longer QCOW2 because QEMU NBD already translated the QCOW2 part of it. What we have is basically a block volume. It's raw. It's flat out a block device. So we can run the same prepare operation. We give it the file where we mounted the QEMU NBD and draw, and voila, we get our connection, and we can now start running immediately with the image that is actually a QCOW2 image. This is almost good. It's not good enough. The main issues here are, one, we lose sparseness. So all zeros are actually being read out from the raw device. Because it's raw, there's no information on where data is and where data isn't. So it's just scanning the entire volume, reading everything, including zeros, and writing them over. So they move over the network. They're actually written. They take up time. Maybe they'll be garbage collection. Maybe not. Another limitation, which is actually a limitation here too, is suppose so I did this prepare. I can now access my volume, and now I want to go and access it from another node. That's doable, but you need to remount the source and the target in every location I actually go. So that's a limitation that's in all of these. So to battle this, we introduced live import from an NBD source. So we're adding, rather than I had two formats, the new format added now is NBD. Okay. So the NBD source, basically, you connect to an NBD server. So when you run the prepare, you need to point to an IP and port address, and that's it. It's flexible because it can support a lot of formats. It gives us the ability to use QEMU NBD with just about any format out there, VMDK, VHD, whatever volume type you have there, you can bring it in, as long as it's a block device and it's supported by QEMU. The target is just an IP address and port, so you don't need to mount it on multiple nodes. You can mount it in one single location. If you're now moving along, as long as that location is live, you can also access it live and has connectivity. That's a second plus. It supports sparseness. That's part of the NBD protocol, which is great. So we actually got the sparseness that we were looking for. So we're not moving zeros along, maybe just a bit if they're not aligned at the same block size that NBD and RBD target. And another plus here is basically we're avoiding the kernel. We didn't do this trick of NBD with a kernel client. Rather, we have a user space NBD client talking directly to a user space NBD server. We're avoiding the kernel altogether. So we get better performance on that as well. PR is under review. Everything I said about the previous PR, if this is interesting to you, so this is also in play. So I'll do a very short demo just to get the feeling of this. Everything, the talk is, it's alive. The demo is actually dead. It's not a live demo. So I'm just going to replace things. So here's our dead demo. Okay. So what I'm showing you is I have a QCOW2 image sitting locally here. Let's look at the information on it. What you can see is it's a 2 gigabyte image, but it's only taking actually 152 megabytes of space. And we want to move it over. So let's first call the QEMU NBD command. We're not mounting it locally. We're just setting up the server. So that's step number one. And now we'll create this JSON that is the input to the live migration. And what we have here is raw. That's the format. And the type is NBD. I was wrong there. NBD is actually the source, and the format is raw. We keep the format as raw. And now we can actually run prepare using this JSON. So we're running the prepare command. At this point, you can already start running with the volume. Once the prepare finishes, you can start running, reading, and writing to it. If we list our RBD images, you can find it down here. It's 2 gigabytes of a volume, 0 bytes used, because nothing is there. It's all in the source. Now I'm going to run the RBD migration. With the live, you'll actually see the numbers running. It's pretty quick for this size of 452 megabytes. And once it's done, I can do commit, which cuts ties with the original one. And if I look at the volume again, you can find it here. It actually has 156 megabytes. So almost kept all of the sparseness, and that's, so we'll quick that demo just to get the feeling of it. So that was bringing from an external source and why we needed this NBD source that we added. So I'll go to the third, maybe most complex setting here, which is backup and restore. So it's backup and instant restore, and that's the big difference. So when we set up our goals for backup, these are the goals, basically. For backups, we wanted it to be differential backups. So you're not moving all of the image out every time. You want to move only the changes that have changed since the last time. And we want to move it to, I wrote cold cheap storage. Actually, I mean object store with an S3 interface. So it's not tape or something like that. I'll use cold storage because it has slower performance. That's just the reason I'm calling it cold. But it can be more than just that. On the restore side, we want it to be instant. And instant means that even though the image, the backup is sitting externally on S3, I want to immediately be able to start running on it. I'm willing to take the hit of the latency that I incur with running on the colder storage. So initially, if you start running, all the IOs, all the reads are going to get latency of an object store. It's not very nice, but it's only going to last as long as the migration is on. Once the migration finishes, I get the performance that I really need. And this is kind of a feature that is given by many cloud vendors. With Amazon, you can back up EBS to S3 and immediately start running off your S3, and initially the performance is bad. We're trying to emulate the same thing here with Ceph and RBD. So some challenges in actually doing this. And the challenge is, well, the natural thing, how do you take snapshots out of RBD and back them up somewhere? And there's a tool for that. It's export, RBD export. There's version 2, which supports diffs. And it's going to write stuff in its own format. And you can do import v2, and it'll bring things back up. And that's great. The problem is that it's not instant restore, and it cannot actually support instant restore. The reason why it cannot support it at all is we need a format that allows random access. Because with instant restore, what we had is when you get a read to a specific LBA, you need to be able to get this specific LBA 17 from the source. If you don't have a mapping of where 17 is, you don't know where to get it. With the export format that Ceph has, you're going to have to scan basically the entire thing to find LBA 17. So what formats do give us random access? Obviously raw. Raw is just, you write everything down, very expensive. We don't want to write the full 2 gigabytes from the previous example. But there, LBA 17 is at address 17. That's easy. Other formats which are thin include, for example, QCOW2. So anything that has an index. All of these have kind of, there's the data area and there's the index area. You first load the indexes, you go and you can find specific addresses. So we need one of these formats. So what I'll show is basically a POC that we did for a specific use case. And the POC uses QCOW2 as the base. And you can go away from that or do other things, but it's just meant to show how to use basically this live import in order to get what we want. Okay, so for backup, we're using basically there's an API diff iterate with RBD, It's actually used by the export v2. So go low level, and it's just going to give you whatever has changed between snapshot A and snapshot B. And you can read all of that out. And what we did in our POC is we write that into a QCOW2 image. And the image contains only the changes. QCOW2 images have this notion of a backing file. So you have just the changes in one file, and then you point to the previous file and the previous file and the previous file, and you can get a chain. And it's going to traverse the chain until it finds the LBA it's looking for. So that's a pretty simple operation to do. And so every time we have a snapshot, we take it, we do the diff iterate, we create a QCOW2 file, and we move it onto cold storage to S3, basically. Just at the end, and add a pointer to the backing file. That's easy to do. The restore, so this one got a bit complex, not as nice as we'd want it to be, but we did the following. So we have the S3 object store. We mount it using some fuse, our clone, some fuse device that brings us files from an object store, and set up QEMU NBD on top of that. So you get, QEMU NBD has access to all the QCOW2 files. They're sitting in S3. It's going to parse all the QCOW2 files for us and create an NBD server. And then we simply do the prepare using raw and the NBD source. And this solves all our issues. So this is actually going to work. It's actually, I mean, not terrible in terms of the performance that we actually saw, but I don't have any measurements to show. I should point out that if we had a full QCOW2 implementation, we could use QCOW2 format and S3 source and forgo all of that. There's a reason why we don't have a full QCOW2 implementation. There's no library supporting QCOW2, so in order to add one, you'd basically have to recode the QCOW2, and any new change or fix or something in QCOW2, you'll have to add that. And you'll have to do that for every format. So it's a bit cumbersome. I don't think it's going to happen. So for now, we're working with this NBD format. Okay, so that's kind of what we can do with it today. What's next? I'll finish with what's next. First, let's get the PR that's upstream from what we have already. That's number one. We'll try and get that done, and then this can actually be used widely. The second is there's many possible improvements to do in this realm. Right now, we don't have the capacity to do any of these, but if someone is interested, I will be happy to talk. So support cluster-to-cluster migration of clones is one example. On the backup restore side, I think it's a bit more interesting. There's work that can be done, and I don't think it's far out there in terms of the complexity. So if we can add an index to the native Ceph export format, and we've already set out the design for this, so it's nice. The format just spills everything sequentially, so you can actually take down one block, upload it to S3, and then add a multi-part upload, add another part, and at the end, all you want to do is append at the very end an index of what you've had, what you've seen across the whole image. And now, if we actually add support for this format with this index into the live import mechanisms, then you could go directly using the S3 interface and fetch everything from a native Ceph. So we'll cut, again, I don't like all this noise of the stack here. Would be much nicer if you could go directly to S3 on the instant restore, and you could also go directly to S3 basically on the backup side. So that, with the export v2, I mean, modify it to write directly to S3, that definitely is doable. So that could make things a lot nicer and easier for everyone. Yeah, so that's what I have. So thank you, and I'll be happy to take questions.
I have a question actually. When you do live migration from one cluster to another, is there any latency requirements for the live migration to be usable?
I mean, I think it depends more on your application. If your application has latency requirements, then yes. Again, it's what are the bandwidths? I think from a Ceph perspective, there's no problem.
So what happens? Oh. Maybe sit here. No. What happens? Can you resume? But if you lose a connection to the source, can you actually resume the operation, or how does it work?
Yeah. It's just gonna basically everything is idempotent here, and you're doing the background migration. It's just gonna pick up, and I mean the migration basically says, do I have it? What it does is it at the target? Great, skip. If it's not, go and fetch it from the source. So it's all idempotent. You resume, you can restart. Everything fails, you run on.
You need to stand behind the microphone.
Okay.
So would you also consider a mode where you basically don't ever call the execute and do the background migration, but basically do on every, when you actually read, basically bring it over?
Yeah, so that's what I mentioned kind of regarding, I think, cluster to cluster migration. You can also do that. With backup, I think, like, the big part of instant restore is when you have a lot of images, even if they're relatively small. If it's a small image, no problem, wait as much as it takes to restore. But if you have a lot of them, I mean, thousands of volumes, some big failure, you don't want to start bringing all of them, executing all of them together. So you can just do the prepare for all of them, and then not execute and start running, and whoever is hot and actually needs to be executed then. So we don't have the mechanism today to actually sense, oh, this one we did have an IO on, let's run the execute. But that would be neat. I mean, as soon as the first IO hits, you bring it, but you also set off the execute, and then you get a restore which actually takes into account what is hot and what is cold. That would be really nice. Yeah.
Once you announce the upstream, so will there be any kind of walkthroughs or how-tos kind of documentation in the Ceph documentation website or somewhere else?
So right now it's in the Ceph. So everything that is not upstream, all the Pacific stuff is already documented on the website, right? And yeah, I'm assuming everything will be documented on the Ceph website.
Okay,
yeah.
Thanks.
Thanks. One question about the S3 backup and restore thing. So you said that you are exporting basically the diffs with respect to the previous backup in QCode format, and then on restore you are able to traverse all of them to access the logical blocks that you actually need. Are you basically have a depth of one QCode image only, or you're able to reference instantly?
No, you're able to reference as long a chain as you want. That being said, it's QEMU NBD that does all the work here. So this is whoever is parsing the images, the chain. So QEMU NBD is doing the work. I have not tried it personally, but accounts say that when you have a long chain of backing files, and it doesn't matter if it's on S3 or not on S3, performance suffers mightily.
Exactly. So
Yeah.
my question was actually, you may hit the situation where you just have 100 round trips to S3 because you have to traverse basically a stack of snapshots, which is 100 snapshots deep.
Yeah, so definitely the right way to go with either compact them
Yeah.
or once in a while do a full backup and then
Okay.
diffs of that.
Just one comment on his question. I mean, we have written, I think, a few years ago, a tool that you can offline merge an image with a delta diff, and that you can upfront and say, okay, then you have your original image.
For QCOW2 or for the
No,
Ceph-
from
for the
RBD delta
Yeah.
export, and then you can merge it offline without a Ceph cluster. So
Yeah,
then you
so-
can offer it.
So with Ceph export, that's great, but we don't have the index there. If we
Yeah.
do the Ceph export, that's going to be more challenging because now you need to merge indexes as well. So that's going to be a bit trickier. Today, I think it's pretty straightforward
Yeah.
to merge Ceph exports.
Yeah, and the other thing, I mean, when you lose connection to the other side, and you have already written something on to the other side, I mean, how should the client access the data? I mean, normally it should stall because you cannot access the written data on the other
So-
side in your migration process.
On which side? So
On the target side, I mean, if you write to the target side, you lose connection to the target side. How I should read the data that the client has written?
So you need to remount, and if the write has actually taken place, then it's written to the OSDs in the backend, and if you remount it, it's going to be there. If it died in the middle of a IO, that's same as any IO that you write to Ceph. So it's not different than any other scenario.
Okay, thank you.
Anything else? Oh, thank you very much. Have a good coffee break.